Now we know that we have to control V and F to get the maximum torque at whatever the rotational speed. So now we will learn how to control V and F. There are several methods, right? So this is one method. So this is called here you have a thyristor rectifier. This is the thyristor rectifier. This is 3-phase supply. This is only a symbol. So here you have 6 thyristors. This is a filter circuit comprised of inductor and a capacitor, and there you have 3-phase inverter. This is called a square wave. A square wave means you generate square wave for this induction motor. VSI means voltage source inverter. This is a voltage source inverter with controlled rectifier. This is the rectifier. Since we use thyristors, this is controlled. So why we need controlled rectification? Because we control V using thyristor, full wave thyristor rectifier. We control frequency using this inverter. You switch the IGBT, so thyristors, and you can change the frequency of the square wave signal, square wave output. Thyristor rectifier controls the voltage, inverter controls the frequency. Now if you concentrate on this filter circuit, here you have an inductor and a capacitor. This inductor prevents sudden increase of current. This capacitor prevents sudden increase of or decrease of voltage. Now if you write formula for the inductor, here you can see this is VL. VL is equal to L di by dt. Sudden increase means for small amount of time this I will get a higher value. That means di by dt is very high. It's like infinity, but the voltage across this inductor shouldn't be infinity, so it blocks sudden increase of I. If you take this capacitor, the formula for capacitor is this, or you can use this as V is equal to 1 over C integration I dt, or you can say I is equal to C dV by dt. As same as this one, if you take this capacitor formula, sudden decrease of V is not allowed. This gradient will be minus infinity. So the current through the capacitor should be infinity. So it doesn't happen. So it blocks sudden decrease or increase of voltage. So you filter those uh, ripple currents like these ripples, and filter the input values, filter the output values. This is the block diagram of the circuit what we have discussed previously. Here you can see three-phase AC mains, voltage, line to line voltage. This is three-phase line to line voltage, maybe 400 volts, 50 Hz frequency. So you supply that wave to full wave thyristor rectifier. So AC becomes DC. So here, if you change the firing angle alpha of the thyristors, you can get variable voltage with small ripples. So using filter circuit, you can take smooth voltage, then you apply that voltage waveform to full wave thyristor inverter or an IGBT inverter. So using that one, you can get this kind of square wave signal. This is phase to neutral voltage, A phase to neutral, phase to neutral voltage, and you can derive line to line voltage as well, leg voltages. We'll discuss those things later. Using switching frequency of IGBTs or inverters, you can change the frequency of this waveform. If you quickly switch the thyristors or IGBTs, you can get higher frequency. If you take time and switch the thyristors or IGBTs, your frequency will be low. It's the thyristor inverter waveform, and then you feed it to three-phase induction motor. Now let us see inverter waveforms. We will only take 180 degree operation. So here you can see our three-phase inverter. For simplicity, I removed rectifier, three-phase rectifier and three-phase supply. So VDC is filtered DC supply from rectifier, thyristor rectifier. So here you can see T1, T3, T5, T4, T6, T2. Make sure you name the IGBTs as same as this one. This is a standard way of naming IGBTs in three-phase inverter. Here you can see the induction motor. This is leg A, so leg B, and this is leg C. Voltage from here to here is VAO, this is VBO, this is VCO. So you can see here leg voltage variation. This is 5, 180, this is 360. So if you refer this 3-phase full wave thyristor inverter, let's take that one for 180 degree operation. What do you mean by 180 degree? Each thyristor or each IGBT conducts for 180 degrees. Now here you can see 180 conduction mode. In this mode of conduction, every device is in conduction state for 180. So here you can see T1, 180 degree conduction, T2 again 180, T3 180, T4 180, T5 180, T6 again 180. Where they are switched on at 60 degree intervals. So first it's T1, and after 60 degrees you switch on T2, after 60 degrees T3, T4, T5, T6. Therefore at any instant only 3 devices will conduct. So if you take 0 to 60, only T1, T5 and T6 will conduct. So current will go like that here, and T5, T6, T5 and T6. This current, that current, and all the way from here to there. T1, T5, then T6. (60 to 120) you have T1, T2 and T6. T1, T2 and T6. So in the 0 to 60 you have 2 thyristors from upper half and 1 thyristor from lower half. When it comes to this one, 60 to 120, 1 thyristor from upper half and 2 thyristors from lower half. That's how it works. If you take this one, T1 conducts for 180 degrees. Now T1 conducts for 180 degrees, which means it's like you short circuit this part, right? And here you can see, if you short circuit this part, what will happen? For AO you will be having this VAO. For 180 degrees you have VAO is equal to VDC. So it conducts for 180 degrees and it's not conducting for 180 degrees. So when you open circuit this one, what will happen is, it's 180 to 360. So at that time, if you take T4 is on. See? So you short circuit this part. So this is the complete opposite of this one. T1 is complete opposite of T4. T2 is the complete opposite of T5. See, T2 and T5. You never should turn on this one and this one simultaneously, or this one or that one. Then you short circuit the battery, right? So at that point you turn on T4. So what will happen? When you turn on this one, you short circuit that one. Here voltage is 0, here voltage is 0. So VAO is 0 from here to there. Now if you take VBO, what will happen? So you need to check the state of T3 and T6. So let's check that one. For 0 to 60 degrees. 0 to 60 degrees VBO, T3 and T6. T3 is off, T6 is on. So you short circuit this one. So what will happen? VBO is 0 from 0 to 60. Okay. And 60 to 120, T6 is on. You short circuit. See here, 120 to 180, T6 is off, and if you check T3, T3 is on, which means you short circuit from here to there. This is on. What will happen? This is VDC, this is 0, VBO is equal to VDC. VBO is equal to VDC. As same as that, you can draw VCO as well, like this. Now after deriving leg voltages, you can go for line to line voltages. Now if you derive this one, it's easy to get line voltages. So you can use these equations, these graphs, to get the line voltages as well. Now what do you mean by line voltage? Here this one, VAB, VAC, VBC. This is the induction motor. So these are line to line values. So if you want to get VAB, here you can see VBO, here you can see VAO. All you need to do is you subtract this VAO from VBO. So VAB is equal to VAO minus VBO. VAB is equal to VAO minus VBO, right? So you take this part, this part, VAO minus VBO. So that is VDC. VDC minus 0. Again VDC. Then this one, VDC minus VDC. That is 0. This one, 0 minus VDC. That is minus VDC. 0 minus VDC, then 0 minus 0 is 0. Now you can take another one, VBC. VBC is equal to VBO minus VCO. Then you can again derive this waveform as well. Or you can shift this one by 120 degrees. Here it's 120 degrees here, 120 degrees to right, and you can simply take VBC as well, because this is a balanced supply. Then you again shift this one by 120 and you can derive this waveform too. But I encourage you to draw at least 2 graphs, then you shift whatever the graph to the left by right by 120 and take the other one. Otherwise you may not be able to get the phase sequence, right? So that is how you derive line to line voltages from leg voltages. Now we will concentrate on phase to neutral voltages of this inverter. Now, deriving phase to neutral voltage is somewhat hard. First we will take this circuit and we'll mark this point as O. This is okay. Here you have A, so this is VAO, BO and VCO. So this point is O. And here you can see the neutral point N. So you can write VAO is equal to VAN plus VNO, right? VAN plus VNO, that is equal to VAO. So as same as that, you can write an equation for VBO and VCO. Then you add all these three equations. You can take VAO plus VBO plus VCO is equal to VAN plus VBN plus VCN plus 3 times VNO. For a balanced supply, VAN VBN like this, VAN, VBN and VCN should be 0. This is the neutral point. VAN, VBN, VCN is 0. Then you can write VNO is equal to VAO plus VBO plus VCO divided by 3. Then you can substitute this VNO here. So VAN is equal to VAO minus, we'll take this one here, VAO plus VBO plus CO by 3, this one. Now we can take VAO from here, VAO plus VBO plus CO, same as previous, this one, using this one, and divided it by 3. So using this equation you can derive these 3 graphs, this one, that one, and this graph.